So let me introduce our plenary speaker. Professor Song Han is an assistant professor at MIT EECS. Professor Han is very well known for his deep compression work. Today, he's going to talk about various techniques to improve the efficiency of neural network, including model compression, neural architecture search, and new design primitives. Today, he's going to talk about putting AI on diet, tinyML, and efficient deep learning. Professor Han, please.
Okay, thanks for the intro. I'm very glad to come to the tinyML Summit Asia to present my recent work on tinyML and efficient deep learning. And our goal is to make AI greener and deployable on IoT devices. So today's AI is too big. We need tinyML and green AI. For example, AlphaGo inference is taking almost 2,000 CPUs and 300 GPUs, very expensive electric bill, and the GPT-3 is costing $4.6 million and more than 300 GPU years to train. And according to this paper, training a single AI model can emit as much carbon as 5 cars in their lifetimes. So this is transformer with neural architecture search. So all these algorithms are very expensive. So our goal is to enable tinyML and efficient deep learning from the following 3 aspects. So conventionally, we need a lot of computation, a lot of carbon, many engineers to tune and design those models, as well as a lot of data to train those models. So we want to enable tinyML with less computation, fewer engineers, better productivity, and less data. So to achieve this goal, previously I proposed this algorithm called deep compression, where we can compress an existing model by pruning and quantization. So pruning reduces those redundant connections and redundant activations, and quantization basically use fewer number of bits for the weights and activations. So for less than 50, after deep compression, we can reduce the model size from 100 megabytes to only 6 megabytes. So 17 times compression without losing the accuracy. So pruning and sparsity techniques has gained increased attention since 2015. So it first came in 1990s with the optimal brain damage paper and roughly 200 papers per year. And after 2015, this area begins to boom with thousands of publications these days. So the next question we want to ask ourselves, rather than compressing existing models, can we invent new models that are efficient to begin with? So I'll also introduce neural architecture search, where rather than manually design the neural net architectures, including the channel, branch, resolution, kernel size layers, which used to be a black magic, and it is notoriously difficult to tune, can we automatically design those neural nets to synthesize neural networks to fit the latency, accuracy, and memory constraints? So those neural architecture search to a neural net is like an EDA tool to a circuit. So we designed this algorithm called once-for-all network that can train 10 to the 19th networks at the same time. Therefore, we can easily select different subnetworks without training again for the once-for-all model, so that we can very quickly evaluate its accuracy without any retraining. So we can train a surprisingly large of child networks up to 10 to the 19th for free. Therefore, during the neural architecture search process, we can select a larger subnetwork for cloud device and a smaller neural network for smaller devices like microcontrollers. And this borrows the idea that human brains activates sparsely. This once-for-all network also contains many child networks that are sparsely activated. Those child networks share the weights with the once-for-all network, and they are trained jointly. So that when we have the scenario where users have both the high-end phone and the low-end phones, we want to be inclusive for users who also have those low-end phones. But it used to be very expensive to design neural networks of different sizes. Once-for-all network enables us to train once and get many different child networks for free. This can greatly reduce the design cost and fit diverse hardware constraints. For example, we can select a larger subnetwork for the latest phone and select a smaller subnetwork for older device. And similarly, a larger subnetwork for the full battery scenario. And when in the battery saving mode, we equally don't want to sacrifice the latency and user experience by too much, so we can select a smaller subnetwork. And after that, we can perform evolutionary architecture search by mutation and crossover to select the best fit. And as a result, this once-for-all network, by having both accuracy and latency in the design loop, it is not only efficient for training and search, but also efficient for inference. For example, on ImageNet measured on the Google Pixel 1 CPU, we can reduce the latency by being 2.6 times faster than EfficientNet and being 3.8 times higher accuracy. We also analyzed the Roofline model of the once-for-all network to analyze why it is more efficient than those hand-designed models. The intuition is that computation is cheap, memory is expensive. So the models designed by OFA has a higher arithmetic intensity measured by operations per byte. Okay, operations per byte is higher, therefore it's less memory bounded. Therefore, we can achieve higher utilization and performance even without changing the RTL. So below is the result measured on the Xilinx FPGA, the 03G FPGA. So even on this specialized accelerator, the once-for-all network can improve the GOPS per second, which is the throughput, by a large margin from 48, 44 GOPS per second to 76 GOPS per second. And this once-for-all network works well consistently on diverse hardware platforms, ranging from mobile phones like Samsung phone, Google phone, LG phone, which all have Qualcomm Snapdragon 855. This is using the CPU, and this is using the DSP of the hexagon DSP. So here we can reduce the latency from 18 milliseconds to here is only 12 milliseconds. And also it works pretty well on NVIDIA GPU, Intel CPU, and Xilinx FPGAs. So this once-for-all model consistently outperforms the human design. So this is once-for-all network. So only 595 median max, but achieve 80% top-line accuracy, which is the turnkey solution for this hardware-aware neural architecture design. It also sets a world record in the open division of MLPerf inference benchmark, which was adopted by Alibaba, and they achieved more than 1 million images per second on 8 A100 GPUs. So once-for-all network not only perform well on these edge devices, but also it works really well on the cloud. So this OFA can design a lightweight model, bring AI to mobile devices. So these 3 demos are running on LG phone with Qualcomm Snapdragon 855 SoC. Actually, it's an old phone in 2019, which is a pure software solution to achieve real-time inference on mobile devices, even without AI accelerator. And it can potentially unlock many mobile AI applications like healthcare, smart home, automotive, etc. And we further applied this technique to build this any cost again. So generative adversarial network is very computationally heavy and slow to run on mobile devices. Like in this demo, it's taking 3 seconds to adjust the lady's smile to make her smile and also make her look younger. 3 seconds make it prevented from being interactive edited on our mobile devices like iPad. So we build this any cost GAN with the once-for-all network. We train a super GAN model, and then we can select the subnetworks at low cost, fast prototyping, and we can select larger subnetworks for high quality finalization. So now let's switch to any cost GAN. It's taking only 0.4 seconds now to edit the photo. We can make the lady smile even larger, and also we can make her look younger. Now it's taking a very short latency. This is running on a laptop, MacBook, 2019 MacBook. We can also change the hair color Finally, we can click the finalize button to run the full network, which is taking longer, but getting better quality, and it needs to be run only once. And similarly, we can use this any cost again to edit another photo. We can make this man look older. Again, this becomes real time, although we have to do those pixel-wise prediction, which is computationally intensive. So usually, making the man look older, older, usually associates with wearing eyeglasses. Therefore, we can push this bar to the left to remove the eyeglass and add mustache, etc. Okay, so so far we talk about neural architecture design. How about we open the design space and design the hardware accelerator together with the neural network architecture? So this is a huge design space by including the accelerator design dimensions, the compiler design dimensions, and also the neural network design dimensions. So here we want to offer a turnkey solution that to improve the productivity of machine learning experts and hardware experts to design the neural network topology and accelerator architecture together by using the neural accelerator architecture search, which is a push the button co-design solution. So here we put the neural hardware architecture search in one loop. Okay, so we again use the evolutionary strategy to by doing mutation and crossover to select the best fit of the neural network architecture and the hardware accelerator architecture. So unlike conventional work that can search on those numerical parameters, we can also find new topologies. For example, in this new topology, this NAAS designed data flow parallelizes the output height and output channel dimension, which is very different from the human design. So this KX parallel and array size, buffer size are all chosen by this automatic NAAS search engine. So compared with the human design, we can reduce the energy delay product by 4.4x and even improving the accuracy by 2.7%. So this line of work of neural architecture search is widely adopted by industry like Alibaba, Maxim, Amazon AutoGluon, and Facebook PyTorch. It received the championship in multiple low-power computer vision challenges and also the AI driving Olympic in the NuScenes segmentation challenge. So the next question we ask is, can we go even smaller from mobile AI to tiny AI?
Professor Han, we have a quick question from the audience. So what are the computational requirements for the once for all network in various tasks? How many hours of training and on what machine? He was wondering about this.
Yeah, so the once for all training is usually 2 to 3 times the cost of training a normal neural network. So no matter which machine do you train it on, you pay a one-time cost of roughly 2 to 3x than the conventional single model training, and then you can use it in many devices.
Cool, thank you.
All right, let's continue. So we believe the future belongs to tiny AI. There are billions of IoT devices around the world based on microcontrollers. They are much cheaper and much smaller and almost everywhere in our lives. They are super low cost. Even low income people can have access to democratize AI. And they're of super low power to enable green AI and reduce the carbon emission. But tiny AI is challenging because tiny model design is fundamentally different from mobile model design. So here we are showing the cloud AI running on the GPUs, used to have Ryzen 50, mobile AI running on the mobile phones, where we used to have MobileNet. But for tiny AI for microcontrollers, the resource on a microcontroller, the SRAM readable and writable memory, is 4 orders of magnitude smaller than mobile phones and cloud GPUs. Okay, and the flash, the read-only memory is also 4 to 5 orders of magnitude smaller than the cloud GPUs. So we believe it's high time that we are in urgent need for these microcontrollers like our MCUNet. Deploying deep neural nets on microcontrollers is challenging because there is no DRAM, there is no operating system, no virtual memory. and we suffer from extreme memory constraint. Even for the code segment, no space for the interpreter. And we cannot directly scale existing neural networks. Existing neural networks like a mobile net, they are optimized for the number of parameters, but the number of activation is the real bottleneck. Therefore, we designed this MCUNet to bring AI to IoT devices. MCUNet is published in NeurIPS 20 and also NeurIPS 21. Before that, we used to be able to only do those toy applications on IoT devices, like classifying apples, oranges, and bananas. But with MCUNet, we can even perform those large-scale, real-world applications, like ImageNet-scale applications on these tiny microcontrollers without GPU or any specialized hardware. MCUNet is just so tiny, it can run on these IoT devices. So on the right-hand side is showing the dramatic improvement brought by MCUNet. So the baseline is the MobileNet V2 scaled to fit a microcontroller. It can achieve 54% top-line ImageNet accuracy. But with MCUNet, we can improve the accuracy by 17% to 71% top-line accuracy. So every 1% of improvement on ImageNet is difficult these days. But on the microcontroller, this is still a blue ocean where we can have a huge improvement by using advanced neural network designs. So this is achieved with only half a megabyte of memory, which is tiny compared with the GPU has 32 gigabytes of memory. Mobile phone can easily have 4 gigabytes of memory. So with MCUNet, we can run many real-world applications on this microcontrollers. So this is STM32 microcontroller, okay, which is having the ARM Cortex M7 architecture, so running at 216 megahertz. It has 320 kilobytes of SRAM, only 1 megabyte of flash. And we can run multiple real-world applications like visual waypoints, okay, detecting a person in red. And if there's no person, it'll be in green. It is running more than 7 frames per second. Without person, is in green. And also face and mask detection, faces in red and mask in green. And also person detection, drawing the bounding boxes. So not only classification, but also detection. So this is achieved by tiny NAAS and the tiny inference engine. So there's a global chip shortage. So therefore, we want to better utilize existing chips by using efficient algorithm and software. Okay, so MCUNet basically contains two parts. One is the tiny NAAS, tiny neural architecture search, that perform those hardware-aware neural architecture search using the once-for-all network, and also the tiny engine, which is provides efficient memory scheduling and runtime. So this is showing the performance of MCUNet detecting person using only 30 kilobytes of memory, which can unlock many low-power AIoT applications. So here, the measured peak SRAM here from MCUNet V1 to MCUNet V2, we can achieve only 30 kilobytes of SRAM usage, but achieve 90% of accuracy, which is 4 times smaller than what we did 1 year ago. And with a slightly larger memory, like 118 kilobyte, the accuracy can be boosted to 94%. Okay. All right. So those are general optimization techniques. So let's switch gear to talk about those application-specific optimizations. So apart from those tasks,
can you hear me? So moving to the next topic, one audience is actually wondering if you are open once for all network and MCUNet code and tools.
Yeah, you can check out our website for more details.
Okay, do you have any plans to open it?
It's already on GitHub.
Oh, it's already on GitHub, so it's already open. Thank you.
Yeah, so let's talk about tinyML for video recognition. So video recognition used to be very computationally expensive. So we propose this temporal shift module that can enable this real-time video application, like classifying, putting, covering something with something, like in this video, also moving something, rolling something, etc. This can run at 14 frames per second on a Raspberry Pi. And also we can scale up the distributed training using 1,536 GPUs. So reducing the training time from 49 hours to only 14 minutes. We also work on tinyML for point cloud and 3D LIDAR processing. So those point cloud is highly sparse, which is not friendly on conventional CPU and GPUs. So we designed new algorithms, new hardware, new system across the whole stack to deal with the highly sparse and irregular memory access pattern and reduce the memory footprint. So measured on different benchmarks, we can achieve from 2 to 7 to 6.9 measured speed up. So this is by using our PVCN, which was published in NeurIPS 19 and ECCV 20. And the hardware accelerator, the point ACC, it just appeared at the micro 21. So it was highlighted by NVIDIA as the project of the month by having a 2x measured speed up on different mobile GPUs like Jetson Nano, Jetson TX2, Jetson X Xavier, and Jetson AGX Xavier. So PVCN provides those fine details for small objects at low computation, like detecting person, cyclist, trunk. And PVCN significantly improve the accuracy on those safety critical objects, improving the accuracy of person by 5%, bicycle by 11%, motorcyclist by 25%. So we also deployed the PVCN on MIT driverless, this autonomous racing vehicle. So it improved the accuracy of the cone detection from 95% on the top to 99% on the bottom, also increasing the detection range from 8 meters to 12 meters, while decreasing the latency from 2 milliseconds per object to 1.25 milliseconds per object. And here we also have a real-world deployment for PVCN with this tinyML for point cloud and LIDAR on a full-scale vehicle in the real world. So with fast LIDAR net, we can drive this car purely by using the LIDAR sensors. So originally it ran at only 5 frames per second. With our kernel optimization, it runs at 18 frames per second. And later, NVIDIA also adopted our kernel optimization techniques. So together with fast LIDAR net, it now runs 47 frames per second. And next, we want to talk about tinyML for NLP. So human language is highly redundant. We can prune those tokens with low importance. Like this media coverage is saying human language can be inefficient, right? We can remove human, can be, just leaving 2 words language inefficient. We can still understand the meaning of the word. But pruning the token is fundamentally different from pruning a neural network since the attention mechanism doesn't have any weights. Here we use cascaded token pruning to sort those absolute value of the importance score and then select the least important ones and prune away those less important tokens. For example, this sentence as a visual trait, the film is almost perfect. And then we can prune it to 5 tokens as trait film perfect, and then to only 2 tokens film perfect. And still we can classify the sentiment to be positive. And later we also designed a hardware accelerator to support this cascaded token pruning. So this is the architecture of the accelerator. So 22x speed up with specialized ASIC data path, 3.4x speed up coming from this cascaded token head pruning, and another 2.8 times speed up with the progressive quantization. We also apply this once-for-all network technique to natural language processing. So we build a once-for-all transformer, so we can select a sub-transformer, a larger sub-transformer for the GPU, and a smaller sub-transformer for this tinyML and IoT devices. So on the Raspberry Pi, we can reduce the latency by 2.7x and reduce the model size by 3.7x. We also analyzed what does the attention learn, and we find this diagonal structure, which can be modeled by convolution. Okay? Therefore, we use convolution to model those short-range attention and use attention to just model those long-range attention, which debuts this long short-range attention, LSRA. So this technique can be have a better performance while greatly reduce the cloud computing cost, not relying on those expensive neural architecture search. Even with such human insights, we can design better primitive, which is better, more efficient than AutoML. Okay, so those are several domain-specific optimizations on videos, point cloud, and natural language. And finally, we'll briefly discuss tiny transfer learning. So we not only want to run inference on the mobile devices, but also do training on those tiny devices. So we find that memory is the bottleneck. So we propose this technique called tinyTL, tiny transfer learning, tinyTL, in NeuralRips 20 that can reduce the training memory from 300 megabytes to 16 megabytes. And data efficiency is also important. So for tinyML, an aspect that was missing before is the data efficiency, since collecting a lot of data require months or even years, and along with the prohibitive annotation cost. What if we have a smaller amount of data to train the model? It used to be rendering low quality, like training GANs only using 100 images. That leads to very poor quality. But with our technique, we can generate photorealistic images even with limited amount of training data. So this is our work called DiffAugment, differentiable augmentation, which was published in NeuralRips 2020. So even with a small amount of data, like using only 100 images, it can drastically improve the quality of the generated image. This is the quantitative comparison. So it used to require 70,000 images. Now it's only 100. The performance, we can match the performance using such a small amount of a training image. And it generalized really well from different angles, different seasons, for different image generation tasks. And everything is open source on our GitHub. All right, in summary, we talk about tinyML and efficient deep learning to save computation, save engineer efforts, and save the amount of data. Our goal is to make AI greener, smaller, faster, and more accessible and more sustainable. That's all for my presentation. Thank you all for your attention.
Yeah, thank you for your great presentation. We have a single question from the audience. Would it be useful to develop a TensorFlow specified NAAS?
It's framework agnostic, either TensorFlow or PyTorch. The same algorithm can be applied to different frameworks.
Okay. All right. So you can use TensorFlow for your framework as well. Cool. So do you have any other questions? So if there's no question, I actually have a question. Since you work on this algorithm, hardware and application to improve the AI efficiency, so you have a lot of experience on that. So do you see any trends that which one is actually more important than the other one? So for example, the model optimization itself is actually more important than the hardware acceleration. Do you see that kind of experience?
Oh, it's difficult to say which one is more important than another. I think it's a multiplicative effect, right? If you improve one by 2x, another one by another 2x, hopefully you can get a more than 4x improvement. For example, if you have a superlinear speedup due to something fit in the cache, and then you can have a superlinear speedup if we can co-design the neural network architecture with the inference hardware architecture.
Okay, so how actually did you get some motivation or inspiration? Like in SPArc, you just have some kind of motivation. Although we prune the input itself, we can actually get the pretty similar result. How actually do you start your research?
Oh, so yeah,
Just
a lot of brainstorming, a lot of interaction, talking to people, and analyze what is the fundamental difference, fundamental limitation of the existing work, a lot of profiling, etc. And we actively work with industry partners. So if you're interested in working with us, we are also commercializing our technology. So we welcome more collaborations with the industry partners.
Sounds great. So you hear a lot and you have some intuition, you understand your algorithm, you have intuition and apply that and to prove it. Cool.
We especially want to give thanks to our strategic partners, which really helped us that we can make that event possible. So we have first our executive sponsors. We have ARM, which is the software and hardware foundation for tinyML. Then Edge Impulse, tinyML for all developers. Qualcomm AI Research, advancing AI research to make efficient AI ubiquitous. Sentient, end-to-end deep learning solutions for tinyML and Edge AI. And our platinum sponsors, Reality AI. They add advanced sensing to your product with Edge AI, tinyML. Then also we have Renaissance, broad and scalable edge computing portfolio. Our gold sponsors, Latent AI, adaptive AI for the intelligent edge. Maxim Integrated, enabling edge intelligence. Seed Studio, the IoT hardware enabler. SenseML builds smart IoT sensor devices from data. SynSense building sensing and inference hardware for ultra low power embedded mobile and edge devices. And our silver sponsors, we have Aeon Devices, Deep Light, EMSA, Green Waves, Gravity Inc., HOTG, ImageNet-scale, Geekzo, Rixon Technology, and SAP. So we really want to thank all of our strategic sponsors who will help us. And I hope you all enjoyed it and that we see you again tomorrow. Good evening, everyone.